On the morning of October 13th, 2024, a 400-foot rocket stood on a launch pad in the South Texas desert, pointed at the sky, loaded with more thrust than any vehicle in the history of human civilization. 7 minutes later, that same rocket came back. Not to the ocean, not to a landing pad, not to a field somewhere nearby. It came back to the exact same tower it launched from. And as it descended, two enormous mechanical arms reached out from that tower, grabbed the falling booster in midair, and held it suspended above the Earth. Engines quiet. 33. Raptor motors still smoking from the return burn. The engineers watching from Mission Control in Hawthorne, California, lost their minds. The commentator on SpaceX's live stream said, "What we just saw looked like magic." The other host said, "This is absolutely insane." And Elon Musk posted 3 words on X that captured what just happened better than any technical description could. The tower caught the rocket. Not landed beside the tower, not landed near the tower. Caught by the tower. For the first time in the history of spaceflight, a rocket the size of a skyscraper left a launch pad, went to space, came back, and was physically grabbed by the structure it departed from, intact, ready to fly again. The most unbelievable rocket launch in history was not the launch itself. It was what happened 7 minutes after the launch. And understanding how it happened, and why it changed everything about the future of space, requires going back to the beginning. The rocket at the center of this story is Starship, the largest and most powerful launch vehicle ever built. The complete vehicle stands 397 feet tall when fully stacked, consisting of 2 stages, the Super Heavy booster on the bottom and the Starship spacecraft on top. The Super Heavy booster alone is 232 feet tall, roughly as tall as a 20-story building. It is powered by 33 Raptor engines running on liquid methane and liquid oxygen, generating approximately 17 million pounds of thrust at liftoff. By comparison, NASA's Saturn V, the legendary moon rocket that carried Apollo astronauts to the lunar surface and remained the most powerful rocket ever launched for more than half a century, produced 7.6 million pounds of thrust. Starship's Super Heavy produces more than twice that. When all 33 engines light simultaneously, the ground shakes for miles. The sound pressure levels near the launch pad are violent enough that SpaceX had to build an elaborate water deluge system that floods the launch mount with over 350,000 gallons of water in roughly 20 seconds during ignition, converting the acoustic energy into steam before it can physically destroy the pad. Without that water system, the acoustic waves bouncing off the concrete would tear the rocket apart from below before it ever left the ground. SpaceX spent years failing before Flight 5. The first integrated Starship test in April 2023 ended with the vehicle spinning out of control and the flight termination system destroying it 4 minutes after liftoff. The second test, in November 2023, reached higher, but also ended in destruction, with the stage separation going wrong and both vehicles being lost. The third test, in March 2024, made it to space, but the ship was lost during reentry. The fourth test in June 2024 reached orbit for the first time and survived reentry, though the heat shield tiles showed significant damage. So much damage that Musk described trying to control the ship's flaps as like trying to control it with little skeleton hands. With each flight, SpaceX gathered data, changed what needed changing, and flew again. This is the fundamental methodology of the company: rapid iteration at full scale, using real flights rather than simulations as the primary development tool. The FAA, which must license each flight, spent months evaluating Flight 5's modified mission profile. The license was issued on October 12, 2024, 1 day before launch. The mission plan for Flight 5 was the most ambitious test SpaceX had ever attempted. The primary objective for the upper stage, the Starship spacecraft, was to survive re-entry again and execute a controlled water landing in the Indian Ocean, demonstrating improved heat shield performance after more than 12,000 hours of tile replacement work between Flight 4 and Flight 5. But the secondary objective, listed separately in SpaceX's mission summary, was the one that no aerospace company had ever attempted before. After the Super Heavy booster separated from the ship, it would perform a series of engine burns to return to the launch site and be physically caught by the mechanical arms of the launch tower. SpaceX called the tower Mechazilla, Musk's shorthand for its resemblance to a mechanical Godzilla, and the arms were nicknamed chopsticks. They are enormous hydraulic structures attached to the launch tower, capable of extending outward to span the space where a returning booster would be positioned, and closing inward at precisely timed intervals to grab the vehicle before it could fall. The arms operate through a combination of hydraulic actuators, real-time sensor feedback from the descending booster, and autonomous control algorithms that SpaceX had been developing and testing for months before the flight. If anything in the system had gone wrong, a sensor reading out of tolerance, a hydraulic pressure anomaly, an off-axis approach trajectory, The flight computer would have directed the booster to perform a contingency water landing in the Gulf of Mexico instead. The catch was never guaranteed. It was attempted only if thousands of distinct vehicle and pad criteria were met in real time during the booster's descent. Liftoff occurred at 7:25 a.m. Central Time from SpaceX's Starbase facility at Boca Chica, Texas. All 33 Raptor engines lit. The full stack lifted off the pad smoothly and climbed through the blue Texas sky. Thousands of spectators had gathered on the beaches near South Padre Island, miles away, to watch. The vibration from the engines was felt physically in their chests at that distance. 2 minutes and 47 seconds after liftoff, at an altitude of approximately 69 kilometers, the hot staging ring, the mechanical interface between the Super Heavy booster and the Starship upper stage, was jettisoned. The ship's own Raptor engines lit while the booster was still firing, pushing the ship away and upward while the booster began its own sequence of engine burns to arrest its upward velocity and point itself back toward the launch site. The boostback burn lasted approximately 27 seconds, using a subset of the booster's engines to reverse direction and begin falling back toward Boca Chica. Then the booster coasted, high over the Gulf of Mexico, falling back through the atmosphere. It was oriented heat shield down, using aerodynamic drag to slow its descent. As it fell through the lower atmosphere and the air thickened, it performed a flip maneuver, reorienting to point its engines downward, and began its final landing burn. 13 Raptor engines lit for the landing burn. Not all 33, just 13, giving the booster enough thrust to slow its descent while remaining controllable. The booster's guidance system was tracking the tower's chopstick arms through sensor fusion, combining GPS data, inertial measurement, radar altimetry, and optical sensors to determine its position relative to the arms with centimeter-level precision in real time. As the booster descended below the height of the tower, it performed a lateral slide maneuver, a horizontal drift of approximately 10 meters to align itself precisely between the arms. The arms were already extended, waiting. The landing burn ended, the engines cut off, and the arms closed. The 232-foot booster, moments after returning from space, was suspended in the grip of the mechanical arms of the same tower it had launched from. 7 minutes and 10 seconds after liftoff, the catch was complete. SpaceX communications manager Dan Hutt said, "What we just saw looked like something out of science fiction." Kate Tice, the other host, said, "In the history of this program and in the history of spaceflight, this is a day for the engineering history books." The crowd outside Starbase erupted. The crowd in Mission Control erupted. And the engineers who had built the system that just worked on its first ever attempt had the expression of people who had spent years calculating that this was possible and were now watching the calculation proven right. The engineering reasons SpaceX chose to catch the booster with a tower rather than landing it on legs, the way Falcon 9 lands, comes down to one word: mass. Every kilogram of hardware that you add to a rocket for landing purposes is a kilogram that cannot be used as payload or propellant. Falcon 9's 4 landing legs weigh approximately 2,000 kilograms. That 2,000 kilograms has to be lifted to altitude on every single flight, even though it is only used for the few seconds of landing. Over hundreds of flights, the mass penalty of landing legs accumulates into enormous cost in propellant and payload capacity. If the tower catches the booster instead, the booster does not need landing legs. It does not need the associated hydraulic systems, the deployment mechanisms, the structural reinforcements at the leg attachment points. Musk has stated that removing landing legs from Super Heavy saves enough mass to allow Starship to carry significantly more payload to orbit on each flight. At the launch rates SpaceX is targeting, eventually flying Starship multiple times per day, that mass savings compounds across every mission and translates directly into cost and capability. The chopstick catch is not just a spectacular engineering trick. It is a fundamental architectural decision about how to build the most efficient, reusable rocket in history. The Starship upper stage completed its own mission simultaneously. After separation from the booster, the ship continued upward on a suborbital trajectory, reaching an apogee of approximately 212 kilometers above Earth. An hour after liftoff, it restarted 3 of its Raptor vacuum engines to begin atmospheric reentry over the Indian Ocean. The heat shield tiles, completely replaced after the damage seen in Flight 4, performed substantially better this time. Video from cameras on the ship's body showed the thermal protection system glowing during peak heating but holding together with only minor sparking from the edges of the control flaps. The ship executed a controlled vertical descent over the Indian Ocean and splashed down at high accuracy near a pre-positioned buoy. A second camera, mounted on that buoy, captured footage of the ship blazing down through the sky and hitting the water. The complete mission, from liftoff in Texas to booster catch at the tower to ship splashdown in the Indian Ocean, took approximately 70 minutes. The reaction from the broader aerospace world was immediate and significant. NASA Administrator Bill Nelson issued a congratulatory statement noting that continued testing would prepare us for the bold missions ahead. including to the south pole of the moon and then onto Mars. The technical community understood exactly what had been demonstrated. SpaceX did not just catch a booster, it proved that a rocket the size of a building can return autonomously to its launch tower with enough precision for mechanical arms to physically grab it in midair. The guidance software, the propulsion control system, the hydraulic catch mechanism, and the tower infrastructure all performed on the first attempt exactly as designed in testing. In aerospace engineering, performing a completely unprecedented maneuver correctly on the first attempt is extraordinarily rare. The Wright brothers flew 100 feet at Kitty Hawk. SpaceX caught a rocket. Both happened on the first try. The practical consequences for the future of spaceflight accelerate immediately after Flight 5. Flights 6 and 7, which followed later in 2025, each included booster catch attempts. Both succeeded. With 3 successful catches across 3 attempts, SpaceX was no longer demonstrating a concept. It was operating a system. The booster turnaround time, the interval between landing and being ready to fly again, began shrinking with each iteration as SpaceX refined the inspection and refurbishment process. The target that Musk has described, a turnaround time of as little as 30 minutes between landing and relaunch, remains aspirational for the current iteration of the vehicle, but the engineering foundation for achieving it is being built with each catch. As of April 2026, SpaceX has performed 10 successful booster catches across the Starship test flight program. The system that looked like science fiction on October 13, 2024, is now a routine part of the launch sequence. The significance of Flight 5 extends beyond SpaceX's own program into the competitive landscape of global spaceflight. The Soviet Union lost the space race partly because it could not match America's Saturn V. America's Saturn V won the race but was never reused. The United States threw away every moon rocket it ever launched, a TA, cost per flight, that made the program economically unsustainable beyond Apollo 17. The shuttle was partially reusable but expensive, slow to turn around, and eventually deadly. SpaceX's Falcon 9 made partial reusability routine and transformed the economics of getting to low Earth orbit. Flight 5 demonstrated that full reusability, complete recovery, and rapid reuse of both stages of a super heavy lift launch vehicle is not just theoretically achievable. It is achievable in practice on the first attempt, with hardware that costs a fraction of what any government program would have spent to build it. Every other rocket program on Earth watched Flight 5 and immediately understood that the economics of the launch industry were being rewritten. The moment that defined Flight 5 lasted about 2 seconds. 2 seconds when the chopstick arms were moving inward, closing on the descending booster before contact was made and the catch was confirmed. 2 seconds that SpaceX engineers had modeled thousands of times in simulation, validated in hardware tests at the tower, and never seen happen in reality until that October morning. SpaceX communications manager Dan Hute summed up what those 2 seconds meant in a sentence that will be in aerospace history books. Even at this day and age, what we just saw looked like magic. It was not magic. It was 15 years of iterative engineering, thousands of failed tests, hundreds of design changes, and an organizational philosophy that treats an exploding rocket as data rather than disaster. It was the product of a company that was told repeatedly by competitors, by government officials, by aerospace veterans, that what it was trying to do was impossible. Flight 5 was SpaceX's answer to every one of those people. A 232-foot rocket, launched and caught by the same tower in 7 minutes. The most unbelievable rocket launch in history, made possible by the most relentless engineering program in the history of spaceflight.